I've been doing in Durham, primarily with Marek Gillins, Matt Middleton, but also with Martin Ward and Nick Stretch. So you shouldn't really expect there to be that much difference between the accretion flow in an active galaxy going on to a supermassive black hole and the accretion flow in X-ray binaries. They should just scale with the Schwarzschild radius. It should all work. So if that's true, then the sorts of things we see in black hole binaries should be seen in the AGM, but on much longer time scales because the size scales that we're dealing with are larger. And where our accretion disk photons, rather than being in the soft X-rays, will be in the UV. So those are the two kind of things you think of that should change between the two. But then we should see the same sort of behavior in the black hole binaries as we see in AGN, or rather we should see the same sort of behavior in AGN as we see in black hole binaries. So what do we see in black hole binaries? Well, what I'm showing you here is an energy spectrum, so going from 1 keV to a couple of hundred keV, showing you the components in the spectrum. There's a small component from the disk in this spectrum, and a large component from Compton scattering, making quite a hard spectrum. And then if you take instead the light curve in this energy band and take its Fourier power spectrum, you get this. And what you see in this Fourier power spectrum that goes on timescales of 100 seconds to maybe 1/100th of a second, as you see, there's a lot of fluctuations going on. There's a lot of power in the variability on all timescales roughly between here and here, but superimposed on that, or part of that, is this lovely sharp feature, the low frequency QPO and its harmonic structure. And it's actually quite hard to make a hard spectrum like this. The sorts of models you think about, an accretion disk is going to make you a soft spectrum, thermal disk sort of spectrum. So how do you make a hard spectrum like this? Well, you can't have many soft photons from the disk intercepting your hot plasma to Compton cool it. So you get forced into geometries that look kind of like this, where your hot plasma, which is going to Compton scatter to make the tail, is physically separated from the disk. So if we do it like this, put the hot plasma in the middle, replacing the inner disk, we don't have a cool inner disk with lots of seed photons. So one way to get rid of the seed photons is if they're not there. And we put it physically on the inside, so not all the disk photons will intercept it. Some of them go straight up. And then, as you watch these systems change, as you watch the mass accretion rate onto the central object change, because these are little black holes, 10 solar masses, and the timescales are nice compared to our observing timescales, what you see is the spectrum softens. So we went from, okay, it hasn't done much here, starts to soften. So just look at this panel first and watch the spectrum tip. So it's gone from something that was like this, where all the energy was peaking, with the energy output was peaking at 100 keV, to something like this, where the energy output is peaking at a few keV. That's quite a big change. Correlated with that, I want you to look at this panel. Watch that QPO frequency move. Well, too far. So we started off down here at 0.3 Hertz, and now as the spectrum softens, you see it sweep across the spectrum. Too far. And it ends up at something like 3 Hertz. So obviously, there's big spectral changes, and they're correlated with big changes in this QPO behavior, big changes in the time scales of which these fluctuations, the variability, the rapid variability occurs. So models to make the spectral change have looked at the idea, well, if we've replaced the inner disk at to make these hard spectra, And then we want to make much softer spectra. Well, we probably want the inner disk back again. The only way to get from here to here is to move this transition radius between the disk and hot flow. If we're moving a characteristic radius, then any timing features associated with that radius, any characteristic frequency associated with that radius will move, and it will move to higher frequencies. And oh look, I just told you this QPO moved from 0.3 to 3 Hertz. And that's quite important because the models that I've sketched out on the right-hand side, they were developed to explain the spectral changes. So in some sense, this prediction about some timing frequencies moving up is a real prediction. And it is what you see in the data. Of course, then you have to ask, what frequency is it that is picked out? Which of all the characteristic frequencies that you could maybe think of that might be associated with this radius, which one is it? Physically, which characteristic frequency are we looking at? It can't just be Keplerian at that orbit because the timescales are much slower than simple Keplerian dynamics at that transition radius. Okay.
Meaning we know that transition radius, right?
No, but if you put in
quote-unquote reasonable values.
you put in quote-unquote reasonable values, then
Okay.
it's like factors of 10 too high.
It is the factor 10 involved here, right? That if it would be Keplerian, that would be about 10 times faster.
Yes. You'd be looking at 300.
I would like to make a comment here. Isn't it so that people who do MHD simulations do see these characteristic time scales connected with MRI, which is roughly always 10 times longer than Keplerian time? Just saying that factor of 10 may be connected to this.
You're referring to the stratified shearing boxes.
Yeah.
Yeah, I think that's true. Axel's dynamo, for example,
Yes,
is about
exactly.
that. And
So just a point that there is a characteristic time connected to both Keplerian and MRI.
Oh, I should then make a comment. This frequency, which in your case is factor 10, in my case it's more factor 30, is dependent on the geometry. So if you have a real accretion disk, which is just a shearing box, then that is the correct prediction. If the accretion disk is actually more like a disk,
I see.
the solution is predicted to be steady.
yeah.
And this is actually my first question to the MRI people, which is, I've seen some power spectra of fluctuations that come out of MRI simulations, and they all keep on continuing up to this dynamical time. There's a lot of power here that is not there in the data, is my reading of what I've seen from simulations. Is that correct? Omer's nodding. Anyone else? Axel, have
Can you repeat again? What is
Okay. So what I'm saying is the dynamical time for the innermost regions. So if your MRI simulations are, in some sense, modeling this thick hot plasma flow, then the MRI simulations, if you take the power spectrum of the fluctuations, they would come across and there would be substantial power up to the dynamical frequency, which is here. This is not seen in real data.
Chris, that's fantastic. I heard of this, but I only now realize how important it is in my battle with Julian Croy about where is the inner edge of the disk. He's wrong.
Well, I mean, he now says this is, his paper with Scott Noble says there isn't a lot of stress on the inner edge of the disk and it all looks really quite...
Because that is the reason. He's saying that highly variable at all time scales. But it is not what data
But that's
shows.
not what the data show. So,
Yeah, but
so
that's
what are we
because,
missing
because the
from our
photons that you're observing are all
simulation?
modified by ray tracing or optimization in that hot flow,
What?
smearing it all
What
out.
are we missing from
I mean-
our simulations?
I mean, has anybody
Homer,
done?
you are not seriously saying that nature is not ray tracing.
No, she is ray tracing. That's the problem, and she's
Yeah.
Comptonizing.
Okay, but then one can do a forward calculation based on any model and calculate the spectrum.
Yeah.
Would you then have more? And I'm looking at Mummy. Maybe you have you're here in this room, perhaps the only person who has such global simulations of turbulence. And you? No, you don't have
Chris.
global then. You have global ones?
All right.
Yes. So then what? So you say the power should be much bigger here. Would you
From
have-
what I
can you
remember
have-
seeing of the
quantify this?
MRI simulations, when they take a power spectra, they have substantial amounts of power up to the dynamical time.
You agree with that? Yeah. But or has it been done, or is there maybe something which?
Yeah, but if you stick a probe in there, measure any fluid variable you like, you see power that goes all the way down to the ISCO.
Yes.
But the photons that you're observing there are produced by Compton scattering of soft X-ray photons from the disk
Yes.
going through this hot flow, and you're
Yes.
trying to make sure that, and then Compton,
But
and you want to
that's-
detect those
That's
rapid
not going to
fluctuations.
be. That's not going to take your power down
Yeah.
by a factor of 10,
Why not?
What I want to understand
Why
is-
not?
because they travel at the speed of light.
Exactly, that this power, remember the frequencies are comparable to the light crossing time near the ISCO. So, I mean, light crossing
But the
effects
photons
alone
come
will
in
be-
continually,
Yeah,
so that it's bathed in a nice little bath.
yeah, but a little
Photons.
fluctuation that's happening on those timescales can be smeared out.
No,
It's a
I
fluctuation
don't
in
agree with you.
dissipation.
That
It's a
was-
fluctuation
no,
in
no, no.
current. Omar.
No.
You
That-
calculate the fluctuations in the current.
No, but
Yeah.
And that's what does the heating of the electrons, and the constant bath of photons are coming in, and you Compton up scatter.
let me remind you that there are models also, not based on MRI, but based on some general scenarios, like this cellular automaton.
They don't work because of
yes,
the
but
way the variability
I'm
goes.
making another point.
Mhm.
So people are predicting in these models what would be the slope of the power spectrum intrinsically. And then with a few younger colleagues, I calculated how we will see this through, because there is this ray tracing. Slope changes, but very little. So you are right that slope changes, but not from this to that.
I better move on
But
because
there
I've got
is a
some more
little change.
controversy to stir up.
So there is this effect we are talking about, Omer, but not a strong effect.
Well, let's move on to some more controversial things.
It's multiple scattering. I mean,
That happens on the light crossing timescale. That is very short. It's again dynamical. Right, so high frequency QPOs. That was the low frequency QPO. We saw it move across the spectrum. But there are also high frequency QPOs, which kind of have been seen not very often and appear to be in this 3:2 ratio, telling us something about a resonance that's picked out at a very particular point. So there are the high frequency QPOs, which I believe you've had a lot of discussion on, which are seen at a few hundred hertz, and then there's these low frequency QPOs that are seen from sort of 0.1 to 10 hertz. So there are lots of different types, well, at least two main types of QPO, low frequency and high frequency. The nice thing about the high frequency QPO is it doesn't seem to necessarily change that much in frequency, but I would remind you that in GRS 1915, although the high frequency QPO can be seen at the sorts of frequencies that you'd expect if it really did scale with mass, it can also be seen at some different frequencies, still in roughly 3:2 ratio. That you can either see it at sort of 113 and 68, or you can see it at sort of 41 and 67. I would assert that any 3:2 ratio that didn't stay the same in a single object wasn't actually a particularly good tracer of mass, or at any rate is telling us something a bit more complicated is going on. Right, so how do you make QPOs? What physically do they tell us? Well, in the X-ray binaries, what you see is that you have these two components in your spectrum. You've got the accretion disk emission, and you've got the X-ray tail. And this QPO is always associated with the X-ray tail, not with the disk. So it's telling us that, okay, our spectrum shows very clearly we have two components, disk and hot flow. The variability, not just the QPO, all the variability on these very rapid timescales is connected to this, not to this. So there are big fluctuations that take place in this, which do look very like the MRI fluctuations. You have these big magnetic field reconfiguration geometry. You get a lot of fluctuations in these MRI simulations, though as I would say, I think you get too much fluctuations. But what we see is the QPO is associated with this. So the other thing we can take from the data is that we see these QPOs most strongly where you have where you would draw the geometry for the spectrum where the disk is quite a long way in, where you've got quite a strong disk together with the X-ray corona still. And so if I were given to speculation, which of course I am entirely given to speculation, I would say that when your truncation radius for the disk is out here, and your hot flow kind of extends over a large range of radii where you have the hardest spectra, well, it's quite hard to keep a large radial range doing anything coherent. There's lots of different timescales at different radii. So if you're trying to do something coherent with this big floppy, it's hard. You're not going to get a coherent QPO out of that. But as your disk comes in, you're corralling this hot plasma into a smaller and smaller range of radii. And over a smaller range of radii, it's a lot easier to keep it going at the same time scale. Wherever the scale is, it'll be a lot easier to make it coherent when you're not dealing with a very large radial range for your hot flow. That, I think, is, well, it's speculative. But now, if I were going to be rampantly speculative, I would also look at this picture. And as I look at this picture, I see that there's this overlap region. And if you've got two different fluids in contact, that is an incredible source of turbulence. Is it Rayleigh-Taylor or Kelvin-Helmholtz? Thank you. I always get those two mixed up. So you have two dissimilar fluids in contact, they're going at different velocities. That will be an incredible source of turbulence just here. Maybe we need this turbulence to really drive the QPO. Just a thought. That one I would say is rampant speculation, whereas that one's merely speculative. But the bottom line is, I don't think you'll see these easily in your MRI simulations. Because your MRI simulations don't do this. Your MRI simulations do that. So you've got a large range in radius that you're dealing with, and it's this big floppy thing. And we know from the data that when you're looking at the hardest spectra, where you think you're dealing with your flow over a large range of radii, we know that the QPO is very hard to see. It's very broad, very indistinct. If we can't see it in the data, I don't think we're going to see it very easily in MRI simulations. It's this geometry where you've corralled it into a small radial extent that I think you will see much more easily the QPOs. Because that's what we see. That's where we see them in the data. Right. Let's move on to some more rattle the cages. How controversial can I be? Right. That that was X-ray binaries. I think there's something wrong with the cyan on your projector. Never mind. So what's come out as grey over here is the power spectrum of Cygnus X1 in its high state, where it's more dominated by the disk component. And then here is its power spectrum in the very hard states, where the disk is truncated quite a long way out, and you've got this big, hot, fluffy flow. And then here are some power spectra of some AGN. And you can see that these data are really ratty, because it's very hard observationally to do this, because of the longer time scales involved. But nonetheless, if I take these power spectra and multiply by the mass difference, you'd see that you'd get something very like this. So this is work that especially Ian McHardy has been doing for the last 10 years or so, trying to build up the power spectra of AGN. But I just showed you that in the X-ray binaries there can be this kind of big QPO feature. So we'd surely expect to see it in the AGN as well. The problem is, if you do the numbers, this low frequency QPO is more or less 1 Hertz in X-ray binaries. So if an X-ray binary is 10 solar mass and AGN 10 to the 7 solar mass, multiply that by 1,000,000, we're looking at a time scale of 10 days. So if we need more than 10 cycles in order to see it, we're talking 100 days observations, and that's not going to happen now, is it? So if instead we were looking for the high frequency QPO, then that would take us to a couple of hours. That's much more doable in terms of an observation length. But remember, most X-ray satellites are in low Earth orbit. What's the period of a low Earth orbit? 1.5 hours. That's not going to work. So people had kind of looked for AGN QPOs, but they weren't that devastated when they didn't find them, because it's going to be very difficult. Nonetheless, various people had claimed that their data showed this, but none of them really made it past any 95% significance test. The problem being that power spectra are inherently a rather difficult statistical area. There's a lot of fluctuations in power that you expect just from the statistics of the process. And then it becomes very tricky to estimate the significance of a feature on a continuum noise spectrum. So a lot of the problems have been taking a light curve of an AGN. This is Markarian 766. So you get the data like this, you fit a continuum noise power to it, you maybe see a peak sticking out above that noise power. You've got to ask, how significant is that peak given the statistical fluctuations you expect in power spectra? But this can be done. Simon Vaughan especially has made some very nice statistical models of how to do this. And here is the 90, that's the 3 sigma significance, that's 99.99%. And you can see that these features that people have claimed in this object really aren't going to go for it. The only exception to a really significant signal is the one that was claimed maybe 10 or 15 years ago from a galaxy called NGC 6814.
Thank you very much.
Which turned out to be a cataclysmic variable in the line of sight, which just shows you need actually advances in instrumentation to actually do this. If you have a detector who looks at that kind of portion of the sky, there can be other things in that kind of portion of the sky. Can't imagine who might have been associated with the 6814 detection, but there you go. I find it very ironic that I'm the one who finds the real one, on the group that finds the real one, rather. So here's the light curve of this AGN, and actually, even looking at it like that, you think, that's an odd light curve. Gets even better when you smooth it. So if you just do a boxcar filter on this, you can see there's quite a lot of, okay, we'll do it on the troughs. There's a trough there, and 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 count them off. And what you see is that actually it remains remarkably coherent over the last part of the light curve and kind of loses it a bit down here. So this is showing us that it is quasi, not periodic, since it does kind of lose it down here. But if we take this last 2/3 of the light curve and fold it, what you see is this fabulous sinusoid, and its period's about 1 hour. So let's just check. It's not a cataclysmic variable in the line of sight. Can't think why I might want to be sure that it's not a cataclysmic variable in the line of sight. Here's the Sloan Digital Sky Survey image. Here's the AGN, and now, of course, our instruments, our X-ray instruments, are imaging, so we can put the X-ray image on top of the Sloan Digital Sky Survey, and that's where the X-rays are coming from. So it is not a cataclysmic variable in the line of sight. To do that once is misfortune. To do it twice and be careless. So here's the power spectrum of that last 2/3 of the light curve. Here's the broadband noise power. Oh, look at this. Highly significant. It goes above Simon Vaughan's significance limits. Chance probability is 10 to the minus 7. Even using Simon Vaughan's, we are going to do our statistics properly. Here's the significance plot at the top, which I can't read, but it's pretty obvious. So there is a really statistically significant feature in this light curve. But then you can say, well, those statistical techniques, they depended on looking at the significance with respect to a single power law broadband noise continuum. Maybe it's not so simple as a single power law. Maybe there's a break or something like that that's distorting our significance levels. So you throw a Monte Carlo noise generator at it, you get the same answer out for a single power law, but then you can do a broken power law. You can say, right, let's assume that we have a break at that periodic feature timescale. That would be the worst possible case, and it's still stompingly significant. So there really is a significant signal in this AGN light curve that is telling us about a QPO. So we know it's significant now, so we have to say, what is it? So the bottom line is we've got a QPO. We know there are QPOs in black hole binaries. Here's a QPO in AGN. So this strengthens our prejudice that we came in with, that AGN and black hole binaries really are the scaled up, scaled down cousins of each other. But which QPO is it that we're seeing? Is it the high frequency QPO? Is it the low frequency QPO? Or is it some completely different type of QPO? Well, you might expect the frequencies to scale with mass. So we need to know the mass of this AGN black hole before we can do that scaling. And this particular AGN is of a type called a narrow line Seyfert 1. And narrow line Seyfert 1s are notorious in being difficult to estimate the mass. There are various techniques now that people can use to estimate the mass in active galaxies. They can look at the stellar velocity dispersion, or they can look at the broad lines, they can look at the total light from the bulge, and these all give very different answers. Normally, for broadline AGN, they're all there to within a factor of 3 or 5. For this particular narrow line Seyfert 1s, if you do these different methods, your masses change by a factor of 30. That doesn't help. If our range is like this, then when we come to scale up, we have an uncertainty of a factor of 30 in the mass. We need some other way of trying to understand what's going on. So, what else is special about this object? Why are we seeing a QPO here when I convinced you earlier on that actually we don't expect to see any QPOs? So, what else is special about this object? What might be causing the QPO? Well, if you look at its spectrum, its broadband energy distribution, what you see I've kind of picked out with this red line. And in the green, I've put the standard AGN ionizing continua that's in cloudy, what it thinks a typical AGN ionizing spectrum should look like. This is completely wacky. There is a point here. This is this huge, enormous, peaking in the extreme ultraviolet part of the spectrum. This is a pretty wacky spectrum. It stands out even amongst narrow line Seyfert 1s, which are well known to be pretty extreme objects. It's the, if you think of this as the accretion disk, it's the highest temperature accretion disk. If you look at the X-ray spectrum and work back, so here's your X-ray spectrum down here, work it back. Even in the X-rays, there's this enormous rise to soft X-ray energies. Yeah, so you look at this and you think, well, I don't think actually I'd like that to be a normal AGN. I think I'd actually like this to be Super Eddington, because you don't see spectra like that every day of the week. This is really wacky. So let's home in on the X-ray part of the spectrum. Excuse me. And this galaxy I've shown in red, there's another one in blue, don't worry about the one in blue. So this is what I was showing you before, that if you look at the harder X-rays, then extrapolate those down, there's this enormous rise to soft energies. And this goes by the name of the soft X-ray excess. And REJ has got the biggest soft X-ray excess you've ever seen. So what is this soft X-ray excess? This is the obvious thing to ask. And actually, it's not just around in objects like REJ. Here's a compilation of narrow line Seyfert 1s. And what you see, here's the UV, and here's the X-ray region. What you see is actually they all have some sort of soft X-ray excess. Let's take this one. Those of you who know your black hole binary states, you'll say, oh, look, this looks like a disk and a bit of a hard tail. This looks like a high soft disk-dominated state. But there I'd expect my tail to just be straight, rather than bendy like this. So if you look at this, the hard X-rays kind of curve up like this, and then the soft X-rays slide away. And there's a bit of a soft excess. And it's in all of them. Look here. That's here. This one's pretty ratty data. Look at that. Just this little subtle curve, this little subtle rise. There's another. They all have.
And wait, I'm finding I'm getting very angry now, because not at you. So the model that we've been sold for years is they take that little dip, put a power law through there, put reflection on the right, and put a soft excess on the left, and that's the story we've been sold. Okay.
Right, let's have some more. I wouldn't want you to think I was not showing you. It's like everywhere. Look. Here's the hard, here's this soft little rise. But in general, what you see is the amount of power in this soft rise here, pretty pathetic compared to the amount of power you need in the disk, to the amount of power you think you've got in the disk. Look at this. Little subtle rise here, huge big disk, I can't even reach it. Except the smarter among you, or those with bigger eyes, now there's a good point, those of you with good eyes will have noticed that there are a couple on here that look a bit different. Well done, you've spotted our friend. Here is REJ 1034, where here's the disk, and here's this rise, and the amount of power in this rise is kind of comparable to what you think you've got in the disk. Remember I said its spectral energy distribution was a bit wacky, even amongst the wacky objects. Well, you look at these compilations, and you can see it. So, but the thing you can see is, well, they've all got some sort of soft excess, even if it's a much weaker feature. And it always seems to be happening at the same energy. You can characterize this by fitting it with something with a temperature. So I take this and I fit that with something that's kind of thermal. There's like 20 AGN there. Their masses range from a few by 10 to the 6 to nearly 10 to the 9. And this kind of energy of where this soft X-ray feature comes in, dead constant, varies by less than a factor of 2 between these objects that differ in mass by over 2 orders of magnitude. Maybe not. If this is connected to the disk, here's what we think the disk temperature should be intrinsically. It has no connection to what we think the disk temperature should be intrinsically at all. So this makes you think, nah, maybe we don't believe it's some form of true continuum. Maybe it just is a bit of a distortion on the spectrum. As Omar was just saying, maybe it's to do with some absorption or reflection, something to do with atomic processes because they give us a fixed energy. Don't worry, we will get back to QPOs in a bit. So if you look at absorption opacity in the X-ray regime for partially ionized material, then there are clear kind of dips down when you get to oxygen and INL that take this bite out of the spectrum at the right place. So reflection is just the opposite of absorption. If you have a disk, the photons you don't absorb are the ones you can reflect. So reflection from partially ionized material would have a bite taken out of it where the absorption opacity is high. So reflection from partially ionized material looks like this, with a bite and then a rise again. But we don't want nice sharp atomic features in our data because we don't see them in our data, so we'll smear them by extreme relativistic effects. And that then, we take our reflection and add it to our intrinsic spectrum, then you get this little soft excess. But it is quite little. You can't make a big soft excess in this way, but you can make a little soft excess. To make a big soft excess, you have to somehow lose the intrinsic continuum and only see the reflected photons. And then you can make an enormous soft excess. But plainly, there are other geometries you can do this with. If all we're doing is using partially ionized material, we could have just stuck with absorption. Again, we don't want to see these intrinsic spectral features, so again, we could make our wind just go very, very fast, and then we'd lose them. And then we'd have this nice curvy spectrum that might look a bit like the data, and you could make any sort of soft excess you like. And of course, the real problem is the atomic features. So another way to lose atomic features is to dilute them rather than have them move very fast. So if instead there were some lines of sight that had this partially ionized material and some lines of sight that didn't, then you'd dilute the features down and you'd get something more complex with a smaller soft excess. So basically, everyone likes this idea that atomic features are somehow responsible for this fixed soft excess energy because atomic features give you a fixed energy. And it's hard to get a fixed energy from continuum processes. And the models I've just gone through give you geometries like this. In your reflection-dominated geometries, you can have light bending, or you can have disk fragmentation in order to make the reflection dominant. If you're in absorption, you can make your wind go very fast, or you can make it just a complicated set of blobs and scattering paths and absorbed paths, something horrible. And so these are the models people expected to be behind the soft X-ray excess, even enormous ones like the ones we see in REJ 1034. So how do we tell which one of these is actually happening? We can use the QPO. So if you look at the QPO, and you split it up as a function of energy, and you fold its light curve, at low energies, where that soft excess dominates, You can see it, but it's very small. These are all normalized to the mean in that energy band. As you go up in energy a bit, it gets bigger. If you go up in energy a bit more, the amplitude grows and grows. In other words, the QPO is very energy dependent. It's much stronger at high energies than at low energies. So if I plot the amplitude of the QPO versus energy, what we just saw, the blue points I want you to look at, what we just saw is that at low energies, the fractional amplitude was low, and as you got to higher energies, it goes up. So the QPO does what these blue points show you. The end is very statistically limited, shall we say. Better than using the word dodgy, but I think dodgy might describe the high energy data here. And if you look at the rapid variability, which is about half QPO and half just incoherent fluctuations, you get the green points. Again, rises quite sharply as you go to higher energies, and then, well, who knows what it does out there.
What's the difference between blue and green?
So blue is just the QPO, and green is all the rapid variability.
Okay.
So that includes the broadband continuum fluctuations, as well as this more coherent one. And you can see they're both doing similar things, but there's a bit more variability when you're looking at the total than when you're looking at just the QPO. What a surprise. So that's the pattern of variability that we see from the rapid fluctuations. I won't tell you about that slide, or that slide. Right, so this is what we have to understand. This is telling us about how the spectrum of the QPO is produced. So how does that compare? Here we go. Let's go back to that. So how does this compare with what you'd normally see? Well, it looks completely different, frankly. These are the sorts of amplitude as a function of energy that you see from other narrow-line Seyfert ones. Remember, ours was way down here and went up, and these are just completely different. Doesn't look like anything else out there. So, what are we actually dealing with? What is the nature of this soft excess? What is the spectrum of the QPO? Let's go and fit the data and find out. So the first thing you might think is, well, maybe we've got a disk and some sort of power law tail. First thing you'd think of, it's an absolutely dreadful fit. There's no way this is actually what's in the data. Even a multicolour disk is much too narrow to fit this smooth, continuous soft X-ray excess. You can go to advective disks, slim disks. We said that this one's probably super Eddington. We might expect advection to be important. So if you take the slim disk models that include advection, but assume that everything still thermalizes, they're still not broad enough to fit this broad soft excess. It's quite an appalling fit. The thing you really need is something much smoother, much broader. You can fit it with quite a low temperature Comptonization continuum model. No, we didn't want to be there, but never mind. You can, of course, also fit it with reflection, or partial covering, or very rapidly moving absorption models, but I won't show you those, because when you look at this, you say, okay, if this is really my spectral decomposition, then knowing something about black hole binaries, I might expect the QPO to be in the tail. So I might expect it to be the tail that's got all the variability. And if this really is a Comptonized disk, maybe I'd expect that to be more constant. So if this is going up and down, then out here, we should see constant fractional variability. And then as we come in here, we're getting more and more dilution by this soft component. So we'd expect the variability amplitude to become more and more diluted. That's exactly what you see. So the green points here are the rapid variability, so that includes the QPO, and the blue points are what this spectral decomposition predicts if what you're looking at is a constant low temperature Comptonization component with a tail that bobs up and down. It just goes through the data perfectly. The data have this little kind of inflection here, and that's exactly the opposite to the inflection in the spectrum. It goes through amazingly well. I can fudge it with the other models, but I know when I'm fudging it, and I know when I'm not. We didn't fudge this, we did fudge all the other models.
Are you only changing the amplitude of Comptonization?
I'm only
Sorry,
changing the
tail,
amplitude, yeah.
Not the slope.
I have more free parameters, I could change them
No,
if
I
I
know,
wanted.
but
if you
simple
do the
thing.
most simple thing that
Is it
might be
up
in your head, it goes straight through the data first time. Never seen anything like that before. So, what I'm saying is, both the spectrum and the variability really favour that this really is low temperature Comptonization of the disk, and then power law that sticks out the end. And it's not like we haven't seen spectra like this before, because we have. So REJ, our AGN, is in green. And what I've done is I've taken one of the many spectra of everybody's favourite, we love to hate, GRS 1915, and pulled GRS 1915 by a factor of 20. In other words, I'm saying, I think my AGN is really 2 by 10 to the 6 solar masses. So I pulled it that way by a factor of 20, and it's got basically the same spectrum. And when you fit these spectra of GRS 1915, then we would fit them by saying there is a disk, but then there's low temperature Comptonization that is smudging the spectrum of the disk out. Now, Jeff McClintock would fit these by saying, no, Comptonization always has to be quite high temperature, so I'm going to fix the temperature of my Compton scattering to 50 keV, and then of course you can't make this curvature down here by a 50 keV Compton scattering, so you have to make that curvature by your disk, which means your disk has to be quite a lot hotter, which means of course that you'll get a much higher spin if you take spectra like this when they're actually spectra like this. So if there is some sort of dirty Compton scattering region above the disk, where it's quite optically thick and low temperature, you get this distortion of your disk spectrum, and you take clean disks and smudge them out. And this one really is a better fit to the data than that. And this low temperature Comptonization is pretty much the only thing that will make you this curvature from a Comptonization component. Then you need this low temperature Comptonization, very optically thick, quite low temperature over the disk. So that was right, we've now gone via the nature of the soft excess, which is a hugely controversial hot topic at the moment, but not with you, so you didn't care about that. What you care about is what it meant. What did it mean? Well, it meant that actually I'd go for a 2 by 10 to the 6 solar mass black hole. So now I can scale up low frequency and high frequency QPOs and see where my AGN QPO lies. So the low frequency QPOs going between 0.1 and 10 Hertz. So if my AGN were 10 to the 6 rather than 2 by 10 to the 6, they'd be in the 10 to the minus 6 to 10 to the minus 4 Hertz. Mine is just a bit higher than this at 3 by 10 to the minus 4. So maybe it's a high frequency QPO. Well, they're typically at more than 100 hertz. So I would have expected to see these at frequencies more than 10 to the minus 3 hertz. But mine was just a bit lower than that. It's kind of like Goldilocks. If people know the story of Goldilocks, then it's one is too hard, one is too soft, and one is just right. Well, this is too low frequency, this is too high frequency. We need something in the middle for it to be just right. And remember at the start I talked about that 67 hertz QPO in GRS 1915 that didn't seem to be really one of the standard high frequency QPOs. Well, if you take 67 hertz and you take this mass difference between GRS 1915 and our friend REJ, you'll get exactly the frequency that we see for our QPO. So whatever makes the 67 hertz QPO in GRS 1915, would I put money on the bet? I'd certainly have some speculation that it's the same one that we're seeing in this AGM. And funnily enough, it's GRS 1915 that shows super Eddington flows. Maybe this is some type of QPO we get from super Eddington flows. Now, I've seen the time, and I've gone on quite a bit. But one thing I'd like to do just before we end is to say, okay, we've talked about the QPOs, and we've talked about how we see them in some of the spectral states from black hole binaries. Typically you see them as you go from these low hard spectral states up to the steep power law state. But we also see spectra that really are dominated by disks, and where the disks look very clean. So let's just do a quick whip around the disk spectra. So if I throw out all these complicated spectra that have big QPOs in them, and instead look at just the disk spectra, which may have QPOs in them. This tail is so weak, our statistics are appalling, we probably couldn't easily tell you whether these have QPOs in them or not. So let's just go for what dominates, which is the disk. Here's one source, here's its disk, dominated spectra on different observations, different mass accretion rates. You can get temperature and luminosity of that disk component, and if it really was a disk, you'd expect it to scale just like thermal says it should scale, luminosity to the fourth, and that's exactly what you see. There are clean disks in there at below Eddington rates. You can see clean disks up to something like 40 to 50% of Eddington. You're seeing a disk that's very clean, doesn't have this nasty little Comptonization thing on top of it. And that gets you black hole spin, of course, if you put in all the spectral corrections, which are, they're another talk in themselves, but what is, this line is the best guess as to what you get a low spin black hole. This line is where a maximally rotating black hole would be, so lowish spin on this one, lowish to moderate spin on this one, here's another one, lowish to moderate spin. So you can get an estimate of black hole spin, which at least will help us in the models put some constraints on the spin of our space-time to work out what these QPO frequencies might be physically. So these sorts of spectra at sub-Eddington rates can be very clean disks. But as you get to very extreme sorts of spectra, you do start to see Comptonization, low temperature Comptonization come over the disk. And these are very odd sorts of spectra. And where what you see is sort of continual curvature across the whole spectrum. And that's telling you that there's no clean lines of sight left to the disk. The disk is buried under a Comptonizing cloud that is optically thick. The inner disk cannot be seen directly, or it would be sticking out a long way. It's under a blanket of Comptonization. But this isn't particularly low temperature Comptonization. It's typically 10 or 20 keV rather than 2 or 3 keV that we saw in GRS 1915, these funny states. And when you model it, you can see it's just a very complicated spectrum. So what you can do, seeing the time, so we'll just scuffle through these, if we could do it slightly faster. Come on, machine. So what you can do is say, okay, if we have models of the high soft state where we've got a little bit of the corona left giving us a bit of a tail, suppose we up the mass accretion rate. Maybe we're upping the amount of power in the corona. Maybe we up the optical depth of the corona. As the corona gets more optically thick, it intercepts more of the disk photons. You go from seeing a disk that obviously pokes out the top to having some of these smooth spectra. And now let's go above Eddington. Now we've got to be powering the wind, and that's got to mass load the corona. So now the optical depth of the corona goes up tremendously. And then what we get is we've upped the number of particles more than the amount of energy. Energy per particle comes down, and instead of having this few keV kind of curvy smooth spectrum in this very odd state, we start to make it much more optically thick. And I can make models where I change the mass accretion rate, I increase dramatically the optical depth of the corona, which drags its temperature down, and I go from these very high state spectra that we see below Eddington to something we're calling a ULX state. Because if you go and look at the spectra of ULXs and you fit these models to them, they fit beautifully. Where you have a low temperature, optically thick corona over the disk. It's not a clean disk anymore. I don't even think it's a clean advection dominated disk. I think it's a mess, because I don't see how you can be at Eddington and not be in a mess. So, conclusions. There is at least one X-ray QPO in this strange AGN. Its spectrum is really, really different. We've got this enormous component that peaks in the extreme ultraviolet, and it looks like its tail just continues nice and smoothly down into the soft X-ray regime. It looks like in the spectrum this low temperature Comptonized disk component, it varies like a low temperature Comptonized disk component, so it probably is a low temperature Comptonization component. The problem is that doesn't explain the soft excess in all the other AGN that we see, because I can't think of any way to keep that temperature constant. But in this one, I think it has to be. And then if you relate that to what we see in black hole binaries, well, in black hole binaries we often see the constant disk and the variable tail, but that constant disk is generally cleaner. We do see Comptonized disks in very high states, but the temperatures and the optical depths aren't anything like as extreme, apart from our friend GRS 1915, which is the only black hole binary that does super Eddington for any length of time. So, maybe this is telling us that super Eddington flows are a bit different. Maybe this is telling us that when you have a super Eddington flow, then you have this low temperature Comptonization component which distorts your disk spectrum, and you also have this 67 Hz QPO in GRS 1915 that scales up to match our AGN QPO. Maybe we really, really need to understand super Eddington flows and their variability. Thank you.
Thanks, Chris, for a very interesting talk. Questions, please.
I hit enough controversial topics, come on!
There's no evidence yet for the 40 hertz QPO analog?
Well, we really tried. So obviously, if we could have only found a 3-to-2 resonance, we'd have been golden. But, so when you look at the light curve, the folded light curve, let me get that up bigger. When you look at the folded light curve, they're very sinusoidal. Apart from this one at the highest energies, because you could fit another Fourier component in here that was on a faster timescale. But that's 5-to-1, not 3-to-2. And I asked yesterday, and this is the reason I asked yesterday. So the fact that no one wanted a 5-to-1, I think means I will stand by my statement that that's not statistically significant at all, because I have no idea what it would be if it were real. Let's hope it's just statistical fluff.
So yeah, where does that modulation then come from? What is the idea?
Oh, nothing. She's been selective in choosing the QPOs in 1915 to match the...
Well, there's only two sets of high-frequency QPOs that people have proposed. There's the 4267, and generally you see the 67, and the 42 is a wing and a prayer.
Oh, okay.
Yeah,
So that's
didn't you notice that?
Wow.
Oh, I've got to train you. You've got to watch data. You've got to watch data. Right. Okay. That's at 67. So in that particular one, it's not doing anything. In this one, maybe that's real, maybe it's not. So we've got this. That's why I keep going for the 67 hertz, because it's that you see. In fact, there was a new observation. There's a paper just on AstroPH by Ueda, where he's got new data on 1915. And the spectrum is one of these strange low temperature Comptonized disk. And at high energies, there's a QPO at 67 hertz. So I was very happy with that.
So is 1915 in some other state when it's showing the 113 and 168 hertz, or doing something different?
Again, that's something they don't tell you from the literature, and something we're going to have to go back and look at. So I asked a specific question to Tommaso Belloni. So where it is? That one. So the data I used here from GRS 1915, I asked Tommaso Belloni, in that particular observation, did he see the 67 hertz QPO? And he said no. But you have to remember how they find the QPOs, which is they take their total light curve. And as we've seen, this is in the tail. So it's diluted horribly if you take the total light curve. But then your statistics are horrible if you just take the tail. So it's not clear whether it might actually be there if they'd done a more if they'd looked for it in the high energy light curve rather than in the total light curve.
So I would like to make a comment. It is not that I had a suggestion. It is rather a comment about the difficulty. And it is not a criticism. It is that is hard to understand. These high frequency QPOs in galactic binaries have frequencies which are very independent on anything else by their characteristic to the system. Okay, so they do not change, for example, when the luminosity of the source is changing.
But we only see them in a very particular kind of spectral state.
Yes.
So in terms of where the disk, relative place of the disk in corona.
This is not what I'm stressing now. I'm stressing that there are very characteristic frequency, one frequency because the other one is just in the 3-to-2 ratio. And so it seems that it's this other frequency which Chris said is neither low nor high frequency.
Mm.
It looks like this 67 hertz is also something which is given by the source. And if it would be like you said, which I believe, I like this story very much, I think it's fantastic, that is connected to super Eddington, then it is kind of more difficult to understand for a theoretician why it could be that
Yeah.
it is
Why is it so coherent?
Yes,
When
so
I just
coherent,
told you
exactly.
it was a mess. I said,
I-
look, there's a
I
big
have-
optical depth
yes,
flow.
exactly,
How do you
exactly,
get
yes.
a big
That's
optical
a
depth
fantastic
flow
challenge.
varying?
Yes, yes, yes. That is exactly what I was going to say. It's much more difficult to understand. Coherent oscillations, we are
Yeah.
somehow characteristic.
I agree
of
entirely.
Eddington accretion rate.
But I don't see how a super I mean, I can see what's in the spectrum, unless this is the disk structure, that we are actually just seeing the disk structure, and we're now seeing down to the photosphere, and we're looking at more and more of the disk.
And I tell you why I.
But none of the disk models do
there
this.
is a reason that I see this really difficult, because I could understand that this coherent, the kind of a normal high frequency QPOs result from some coherent oscillations of a cold thin disk, like you said several times. That is what you think follows from the data. And then the 67, I thought, okay, there are a lot of nonlinear effects in oscillations. Maybe if you see oscillations at high frequency, there would be a way to make lower frequency oscillations. Like, and don't laugh at this, it's serious. Like we see, for example, in the ocean, this effect of the so-called seventh wave or ninth wave, that we have high frequency phenomenon, and then by nonlinear modulation, a low frequency. So that is why the every seventh wave, that is kind of understood. That
Those are just beats, right?
sorry?
Those are just beats.
Yes.
Yeah.
Well, that's not really a beat frequency. It is something else.
It's a
It is-
measurement of the size scale of the storm that's exciting the wave.
It's not always storm exciting the wave.
Well, whatever's exciting.
It's the fact that in nonlinear oscillations, frequency depends on the amplitude, and therefore, when you have a wave packet, because the speed of propagation depends on the frequency, and frequency depends on the amplitude, then there is this way of they are moving not with the same all the ways, not with the same velocity. But details are not important. What is important is that we do know
I mean,
about nonlinear effects which are producing low frequency oscillations when you have high frequency oscillations. That's only this general statement. So this 67 hertz was in my mind possibly something which is produced this way. But now we are saying that there is a source which is super Eddington and which has only this middle guide without having the higher. So it must be really intrinsic physically that it is this oscillation which is being excited and not this oscillation being result of excitation of some other oscillations with higher frequency. And therefore I think it's extremely interesting.
But in
because
JRS
it may be, as you
1915, we
said,
do sometimes just see the 67 Hz
Exactly.
QPO.
It may be, as you said, something new, some new type of oscillation.
Which is scary. It's not like we didn't have enough to play with already that we didn't understand. Any more? I must have.
So what does Omar say? You disagree with Marek's statement that it's nonlinear, and you think it should be a
well,
beat?
no, the analogy with ocean waves is.
No, it is not analogy. It is only that if you have nonlinear oscillations, you may have this phenomenon.
Yeah. I'm disputing the
Yeah.
fact that the ocean wave, but that's completely irrelevant to this discussion. I mean, I don't want us to get into talking about ocean waves. But, I'm waiting for Marek to say that it's obvious why this only appears at superheating luminosities, because you're starting to get substantial pressure support in the flow, and you're starting to form a torus or something. I mean,
Yeah, I'm not saying that, Marek.
why aren't you saying that?
Why am I
And
saying-
that only appears at high Eddington range.
Because I'm a very careful man.
Okay.
And then say something. As you know,
But when you have your sketches on one of the first pictures,
but I'm glad that you said this.
But I'm still blaming you for the statement.
yes, exactly. So the blue stuff is essentially pressure supported, right? The blue in your
Yes,
sketches.
it's something like an MRI type
So why
of
is that not
offload.
getting any thicker here? That's exactly what one may actually also ask. If it's already pressure supported, why is it not getting thicker?
Do you think
It
the
may
ADAF
well.
is geometrically thin?
No,
Yeah.
but it's
So
not.
sheets.
It's not a
What?
formal ADAF. It's just a more complicated. It's one of these MRI large-scale height hot flows. So it's got properties that are somewhere between an ADAF, a CDAF, a
Adios.
MDAF, a JDAF, and
There's a
IDS.
jet. There's a jet. You know
There's a
this
jet.
now.
We know there's a jet. There isn't room on this picture to show you what the jet's doing, but the jet behaviour knows all about the hot flow and knows.
But because you are showing this picture, let
Yeah,
me
I'm gonna
repeat
interject
that
here
is
as
the
well.
sweetest part of your talk. No power between low frequency.
Okay,
of
so
the-
Chris,
of
tell
the-
me why
of the
this
wave
won't
to the
work.
dynamical range.
There are two things. The C photons are coming from here.
Yeah.
Well, let's talk about this. Are you optically thin in this flow from here down to the ISCO?
Tau of unity. It's like
All
the
the
worst
radially all the way down?
more or less. It's like the worst possible case.
So it's
to
tau
be
much
in.
less than unity vertically?
I think I would rather have it more like H over R of 0.3. It's pretty quasi-spherical.
I mean, could this be an attenuation effect is what I'm wondering,
No.
partly?
No,
Okay,
Compton
no.
scattering happens on the light crossing timescale. The light crossing timescale is of order that it's even faster than the
But okay,
dynamical
so the
timescale.
other thing that I'm wondering is,
The
yeah,
light
I know,
crossing timescale is milliseconds.
but you're getting, so the observer is going to be seeing photons from these inner regions which are fluctuating on ISCO-like timescales,
Yes.
but from both sides of the black hole, and they're going to be arriving with phase delays. Doesn't that smear out the signal as well? Could that help this?
But remember, those phase delays are of order the light crossing time or the Compton, and that's over here. They're milliseconds. Tens of milliseconds. No,
So it
not
can't be-
milliseconds, microseconds.
So-
Tens of.
No.
No, sorry. No. They are milliseconds.
Tens of milliseconds.
Yeah.
These are 10 solar mass black holes.
Yeah, which is over here. And yet
Yeah.
we're already down by. We've got to start here.
Yeah.
I tell you what does work. Roger Blandford jumped on me for saying this, but it does work. Is if you say, we've got this flow, and there's turbulence generated here. And in fact, there's on the shearing layer, and then there's turbulence generated by the MRI fluctuations all the way down. But you've got that turbulence, and so that's modulating the mass accretion rate at each radius, but you can't modulate the mass accretion rate on timescales faster than the viscous timescale of the flow at that radius. And so each radius will only let through it's like a low pass filter, they only let through the fluctuations that are on longer timescales than the viscous timescale at the radius. And then this is the viscous timescale at the ISCO for a large scale height flow. It works quantitatively. Why aren't you seeing the viscous timescale in your MRI simulations? And why did Roger Blandford have a cow when I told him this?
What did you ask? Why we have not seen the
Yeah, why don't you
viscous
have the
timescale?
viscous timescale?
Yeah. Now, first of all, the viscous timescale is, of course, the dynamical timescale in the disk, because
No.
it's due to the turbulence, which is.
Well,
happening
it's
in the
it's
No.
alpha h over r squared times the dynamical timescale, and if h over r is kind of 0.3,
It's not the omega timescale, no, but it's the turbulence one.
No, and
So that has to be with
I
now I'm
don't know.
forgetting what
I don't know
the
whether you would agree what Julian Krolik is telling
Do you remember?
all the time
You have the P.
himself or when asked. There is no characteristic time scale in this MRI simulation.
Why
He's
not?
producing all time scales. There is
They can't circumvent a
yes, it
viscous
is exactly
timescale.
what I
It
don't
is not
know.
physical.
Oh, well, that could
But,
be.
let me make another comment.
So you always have like a.
Omer, it is for you now. You said
We're now forgetting what we're seeing in the simulations.
What else? Aha! I'm motivating you to do this then.
It is. You said that you was waiting. I will say about this pressure-supported tori. Okay. I didn't, but I would like to make an observation that in several simulations which I have, so I would associate, of course, or I was doing this with colleagues, high-frequency QPOs with this transient torus. Okay. Now I have seen in Chris's simulations 2 transient tori, right? In your simulations, sometimes there is not 1 torus but 2 toroidal structures.
I think the second toroidal structure you're seeing is just a remnant of the initial conditions.
I see. But
You wanted one to be the 67 Hz DPO, one to be good try, good try.
And you said you were careful.
It's my rampant speculation. Is it starting to infect the room?
I'm not saying anything. I'm just asking about the second torus. How serious this second torus is?
The second torus is a remnant of the initial conditions of the simulation.
So what is actually the difference between the blue and the red? Is I mean the red stuff is rotating at Kepler and the blue stuff is very slowly rotating.
Well, not very slowly rotating. It's
slower.
an MRI flow, so it's kind of mostly Keplerian, but.
But then it would be the same speed, and the gas is also the same. So what? Then
Yeah, but
there's
it's
no difference.
in as well as having a V phi, it's got a VR and a V theta,
Yeah,
so it's.
I'm not sure I go for the.
It
You
was
talk about
rampant.
the Kelvin Helmholtz. And
It was
I-
rampant speculation. It was worth a try.
No, but I think it's actually not a crazy idea, especially for the low frequency QPO being associated with that. And I'm sorry to now deviate from the tilted disc, but this is the revelation that we all had at Photostella that after Brian Warner's talk, that dwarf novae oscillations occur in the boundary layer between the disk and the central star, where again you're having a shear. Actually, it's also a shear with a negative angular velocity profile because the inner regions are rotating more slowly than the outer regions.
Yes.
And the same thing is happening in that transition region
Yes.
here.
Mhm.
And they both exhibit, and both of those configurations exhibit very strong QPO.
Yes. I like this very much because in our very kind of non-realistic models of oscillations in fluids, we have problem in exciting a particular kind of parametric resonance, and the reason for this is mainly that initial perturbations have too small amplitude, and then if so it is like exciting oscillations in something which is a thin disk, and if I have now above thin disk something which is very turbulent, I can think that there would be oscillations with high amplitude bumping on this thin disk, and that is why QPOs are excited, because the perturber has sufficiently large amplitude to move up in this kind of Arnold's tongue diagram. So I like it very much. So you said this is kind of a very general way, but it is really very helpful to have a source of high amplitude perturber.
So when you say perturber, the perturber is in the blue stuff or the red?
No, perturber is what is above the disk. Perturber is this.
The blue.
So oscillations, these coherent oscillations are in the disk, in thin disk.
Right.
But this blue stuff is bumping on this disk and excites
Except that it's
But we
strange
don't
because
see the coherent oscillations in the disk spectrum
Why
at
should-
all. They must have such tiny amplitude in the disk spectrum. So how are they then managing to
This is
transport that
another
into
thing.
the flow?
I
I mean, I'm more into the idea. I'm more into the idea that Magnus has been doing in his thesis, which is that you stir up the blue stuff. There's turbulence here, there's turbulence in the blue stuff itself through MRI. You stir it up, you're shaking it in all directions. One of those directions will be vertical, and then once you've tilted it, then a vertical tilt processes round.
But I mean,
That's
it's
mixing
strange, yeah.
many different things
No,
into
no,
one.
no, no, but
Into
Why
one
not?
program.
but look, please.
And that's the
There
low
are-
frequency
there are
QPO,
some-
not the
there
high
are
frequency
some-
QPO.
There are some work, a few works, also very ideal models. One by Paola Rebusco and,
Yes,
and
yes.
Roberto Vio and others,
Yeah.
and another one by Axel Brandenburg, to show that stochastic perturbation may excite coherent oscillations, either in something which is too mathematically general model of a disk, or something you have done in a shearing box, right?
Right, I want
So-
a reaction from the MRI people. I have basically said here to the MRI people that you won't easily find QPOs in your simulations.
But it may be
And we
that
don't.
it is.
Yes.
I mean, that's
No,
we
there's a-
already know that we don't, so.
So
So-
why does that make you happy?
Well, right.
Because she's saying that the reason why we don't is we're missing some key physics.
So
Just
why
in
don't you
simulation.
put some key physics in? Why, these are the geometries
Come
we
on,
draw.
we did put some key physics. We tilted the disk, and now we do see QPOs as predicted. And
Yes, please, please.
Mm.
That's the one you want to model.
no,
So you don't actually subscribe to the WAP disks, and why not?
To what?
No, I think she better.
Tilt the
She's,
discs.
this as far as driving the high frequency. I don't know.
High frequency or low frequency QPO?
He's specifically referring to her mechanism, which is what Ken's working on, where the warp is actually driving it would be a high frequency QPO in this picture.
Yes, but
So you'd have a
let
warp on
me
your thin
remind you-
disk, a little warp on your thin disk, and then that would be.
Well, it even exists inside the simulation that you were
Right.
looking at.
Okay.
Let me remind you that in this context of MRI instabilities which are produced in MAG flows being the source of a perturber and then coherent oscillations are in something else, I think that one may say that we have seen this in MAMI's simulations, because it is what they wrote actually, that they first see these low frequency oscillations, and then there are, which are everywhere, and then there are coherent oscillations of this semi-toroidal structure. So what Chris told us, that it may be that the real story is that there are these MRI oscillations in the blue corona, and they are then bumping on the disk and excite coherent oscillations. It's a very reasonable idea.
I think the person who succeeds in simulating that structure
Will win.
will learn something
Yeah,
extremely
we will get
interesting. Yes. So the first person who does this.
Because it seems.
But you have to, you have to introduce the proper thermodynamics or not,
Yeah.
maybe improper thermodynamics in the simulation to get this
I'd
two-phase
start
flow.
with improper thermodynamics.
Right, right. You just have to construct. It doesn't matter whether it's
Yeah.
realistic or not. You just have to have part of the flow being really able to cool,
Mm.
and another
Yeah.
part of the flow not being able to cool
Yeah.
so much, and then see what you get.
Mm-hmm.
So someone ought to.
But
do it.
I draw a picture like this, and I can see there are at least two types of QPO. There's one type of QPO, you're hitting this little blue thing in all directions, it's very turbulent, so you get some sort of vertical tilt that'll process around, there'll be that long time scale in there. But then you can wobble it, breathing modes, or perturb it up and down, some sort of mode like this, which will be much faster. You look at that and you can see it should have low frequency and high frequency QPOs in it.
Got it?
Still wondering if excuse me, if the geometry in neutron stars is the same, because we tend to focus on the black hole QPOs, but they also exist in neutron stars and are much stronger actually.
Well, it's then just the same, apart from the fact that instead of having this black bit here, you just put a surface. And then you've got a boundary layer. Half your energy comes out in the boundary layer. The boundary layer is also a whisk. So you now have another source of noise generation, because you've got a very turbulent, you've got another very turbulent boundary here. So life is going to get much more complicated.
Are you saying that the QPOs are limited to a spectral state which corresponds to the steep power law state in black holes?
That's where they're strongest. So when you're in, let me bring up, I've got one which does neutron stars specifically, so let me go there. If anyone needs to go, just go, because I can talk forever, you know. So we did this. CFA. Okay, let's go here. So if we're looking at some sort of MRI flow onto a black hole, all that should change is that we now have a surface. So, but then we can get more than half the energy dissipated by the kinetic energy that in the black hole goes straight down the hole. Now will form as a boundary layer. And then what matters is whether that boundary layer is optically thin or optically thin. In terms of the sorts of spectra that we see. Oh, come on. It'll get there. And so you can draw exactly the same sorts of models for what's happening to the accretion flow, the ones that work with black holes, and then you can just put your solid surface and boundary layer there, and that gets you the neutron stars, and it gets you all their spectral evolution, gets you those funny states that they see in neutron stars. They call them wacky names. These are the atolls that do island states or banana branch. Well, island state is just the hard state in black hole binaries, and then you go to a disk-dominated state, which you have to put the boundary layer on. Here we go. Right. So, come on. So in the black hole binaries, I'm telling you that we can make models of the accretion flow where we replace the inner disk by this hot fuzzy flow, which here really looks like an MRIE flow, and then you bring the disk in and you go from these very hard spectra to these disk-dominated spectra. And these work to explain what we see in terms of the spectral evolution. So for neutron stars, all you need to do is put the neutron star surface there, and you put its boundary layer there. At high mass accretion rates, the amount of material pouring onto the neutron star surface means the boundary layer goes optically thick, so it kind of tries to thermalize but doesn't quite get there because there's not a lot of true absorption opacity. So you just stick equal energy in your boundary layer at higher temperature, and that makes you the sorts of spectra you see at high mass accretion rates on neutron stars. So above, say, 10% of Eddington, neutron stars show these curvy spectra where you've got a disk and the boundary layer. At low mass accretion rates, your boundary layer's gone optically thin, so it kind of joins the fluffy MRI and it's all a bit horrid. But yes, what you see in the neutron stars is your QPOs all in here in this boundary layer. And that's where all your variability is as well. The disk stays constant because the disk always stays constant. Did that answer your question?
Wait, so the neutron star QPOs are always seen in the boundary layer emission?
Yes.
So again,
Beautiful paper by Mike Reviuste.
Yeah, I'm familiar. So again, it's boundary layers, boundary layers, boundary layers. It's transition zones between rapidly rotating material and slowly rotating material. That's what we should all be focusing on.
Okay. That'll do.
I mean, is that now the naive conclusion from your talk? it's the transition regions always between rapidly rotating flows and. I mean, you'd like to go more than that, Evie, because you don't see anything from cool flows either, from thermalized flows.
Yes. Yes. So if I'm in this geometry, then if I'm in a black hole, let's go back to a black hole. If I'm in this geometry with a black hole, well, actually, I don't think I can tell you what we see because I can't see the hard tail. But the disk itself does not do QPOs. Does not do low frequency QPOs, does not do high frequency QPOs, does not do any variability on short time scales.
That is one of the possible interpretations. But one can also think that QPOs in neutron star disks are disk oscillations like they are in the black hole disks. However, modulation is different. It is that the accretion rate of matter leaving the disk and hitting the boundary layer is modulated by disk oscillation. And therefore, photons.
But then why don't we see it in the disk itself? Because the mass accretion rate in the disk has to be modulated.
Yes, but it is like amplifier that amplitude in L is greater than amplitude in m dot, although the frequencies are the same. So,
but it has to be amplified by orders of magnitude.
No, by a factor of 10 only, because amplitude.
That's one order of magnitude.
One order of magnitude. Okay.
But I think it's still.
It is not difficult to get.
I think it needs sometimes to be more than one order of magnitude. I have seen disk spectra where the amount of variability is.
Well, but it is never 2 order of magnitude.
Yes, it is.
It is.
Yes.
Okay. I don't know about that.
Okay. Let's try. Okay. So let's look at an animation. The top one shows you the very long-term light curve. This is like 10 years. And here are the pictures you saw before, spectrum and variability. Ignore the rest. So you want to look at just the top, and the black point shows you which particular observation is being picked out. These beautiful simulations are, of course, done by Marek Galinsky. And here we go. Come on. So you see dramatic changes. But roughly what you're looking at, the level of noise is around 0.01 in these units.
Could you remind us what is in these figures?
Okay, so this is the energy spectra, showing you the two components that you can decompose the spectrum into, disk and Comptonization. This is instead looking at the light curve and putting it into Fourier power spectra. The black shows you the total power spectra, the red shows you the high energy power spectrum above 10 kV. And what you see there is lots of noise, but when we switch to disk-dominated states, so watch the spectrum change. I'm starting to see more of the disk, more of the disk, more of the disk. The black one is the one you want to look at. The amount of power here is 10 to the minus 5, whereas before it was, this is 3 orders of magnitude down.
Yes, but I think that it still doesn't contradict what I'm saying, because I'm saying that it is not that QPOs are present in these disks all the time. They are present at some spectral states, if you like in the black hole case.
Yes.
So when they are present, the clock is in the disk and the modulation is in the boundary layer.
To some extent, I agree with you.
I think that at some other times, when we see the disk, there are no QPOs, because the same thing is for the black hole disk.
To some extent, I agree entirely. Like I said in the talk, it's some frequency associated with the moving radius of the disk. But you can also say that that will change the frequencies that you get from the hot inner flow, and we know that all the variability is connected to the hot inner flow. So it somehow seems easier to me to use that radius not just as the truncation radius of the thin disk, but as selecting me a radius in the hot flow as well, the radius which allows the hot flow to be.
It is a fundamental and very important question whether these QPO oscillations in black hole are the same or not the same as in the case of neutron star disks.
Yes.
And there is one piece of information which is coming from the data which to my mind shows that they must be very similar, and that is this 3:2 ratio.
You just said that could be because the moon is made of blue cheese. 3:2
yes,
is generic.
maybe. Yeah, I
A whole
agree
bunch
with
of
you. It's in my mind.
Yeah.
But that's only there statistically.
I
It's
can
not
easily
there
see that people
in individual objects.
who have sharp minds could have different opinion. It is in my mind strong. There is 3:2 here and there. And perhaps I am also psychologically biased because these rational ratios, Wodek and I have seen first in neutron stars, and then we predict that they should be in black holes. So that goes other way around, actually. And what I'm only saying, it is not unreasonable to say that the disks, accretion disks around compact enough neutron stars and black holes should be very similar. There is no reason why not, because this inner edge of the disk, if in both cases is close to ISCO, makes the disk disconnected really from the boundary layer. Therefore, these disks should be similar. I mean, to a theoretical mind, I think that it's a beautiful thing to say. They are very similar, and therefore I am looking for similar phenomena.
And in fact, the
therefore,
picture I just showed you is...
If I can explain behavior of QPOs the same way here and there, then I think it's nicer.
That would be very nice
right?
if we
Okay.
could. But let's explain QPOs and black holes first, because they are simpler.
Suppose that it is not like this, that the modulation mechanism through m dot at the inner edge doesn't work. Then it is a very difficult problem to explain why something which is very violent and not connected to strong gravity is always the same on the boundary layer, and in addition, in one important respect, similar to what is going on in black hole accretion disk. It is just, to me, it is more difficult to say, well, I don't know, but because when somebody says these phenomena are different, it is not that he is making less of an assumption. In fact, it's a very strong assumption to say that on the boundary layer on the neutron star, there are complicated coherent oscillations, because these neutron star oscillations are extremely coherent, look like black hole, and we are just saying we don't know what makes them. It's a very strong hypothesis.
When I was
think
doing
that
this
it's much
section,
weaker to say we don't know, but they are similar here and there.
when I was doing this section of the review and looking at the neutron star QPOs, so when I was writing the review, I came at it with a very, there will be a coherent model. I will only write about stuff that makes sense. You might notice there's very little in the neutron star QPO bit, because there was nothing that made sense in my head. There are 3 contradictory statements in the literature. One is that the kilohertz QPOs are in 3:2. One is that the difference in kilohertz is the spin frequency, and one is that they go as the square root of each other. Those 3 cannot be simultaneously true, so I gave up. It's a mess. Which one of those statements is true? Is any of those statements true? Someone who knows more about neutron star QPOs than me. Answer me that question?
You mean that if you make a frequency plot, they are on kind of different lines? This is what you are saying? Well, I haven't understood
Okay,
what
for the-
these three different statements.
For the kilohertz QPOs,
Yes.
the upper and lower,
Yes,
I-
but okay, kilohertz QPOs.
for neutron stars.
Yes,
So I've read three statements in the literature,
yes.
or at least I have interpreted them,
Mhm.
that these two frequencies for the kilohertz QPOs are related either.
Exactly.
Increase
This is
to
how I
resonance.
understood you.
I've also read that they are related by the spin frequency. One is the spin frequency plus the other.
Yes.
And I've also read that the one goes as the square root of the other. These three statements are mutually contradictory.
So what was the first?
Well, not,
But they all fit the data perfectly.
no, there is some. Let me
Like I
say
said,
that. First
this
of
is a
all-
very short section of the review.
Yes. First of all, there could be some small overlap, so there could
Yes.
be for some sources on these three. But I'm not really telling this. The thing is that these two frequencies are obviously correlated. You see them
Mhm.
at,
You see
at
them
the
in-
frequency plot, and then you see that they are correlated.
Yes.
Okay, and then different people are fitting different lines.
Mhm.
It is correlation is a bit cloudy, so one can fit a straight line, another
Mhm.
could fit a square root,
Mhm.
another one fit another straight line.
So,
That is not important.
Mhm.
What is important is that they are correlated,
so Michael van der Klees, I finally.
and that they are correlated is obvious to everyone.
So I got Michael van der Klees. Would not let him go until he actually said what he thought. That was quite entertaining. So what Michael says is the kilohertz QPOs that you see where this boundary layer is optically thin, up in these sorts of mass accretion rate states, at low mass accretion rates, he says those kilohertz QPOs need not really connect onto the kilohertz QPOs that you see when the boundary layer is optically thick.
Could be.
He
Of
thinks
course,
perhaps there is a disconnect, and what we see here is more connected to what we see in the black holes, and what we see here might be something different.
No problem. I can see.
But
There is no reason to
this
be-
is why I
Exactly.
don't touch
There is
neutron
no reason
stars
to-
anymore. They
there
are
is no-
dirty.
Yes, there is no reason to believe that all high frequency QPOs are of the same origin. Right?
Yeah.
And in this context also, I like very much what you said, that there is a place for another type of high frequency QPO, the super Eddington one.
But yes, in some sense, the model I tried to sell you about Super Eddington, okay, you must have this powerful wind coming off the disk, so you make this optically thick material above the disk, but it's got to be kind of messy, and yet there's this very
Exactly.
coherent
That
QPO
is
in
the-
it,
that
and
is
I
the
think I've
difficulty which I
just
already
drawn you
said.
the wrong
Yeah.
geometry.
Yeah.
So, but something happens when you go Super Eddington. I think I need
I will.
coffee.
Coffee.
Not to put too fine a point on it.
Need to eat. Yes, thanks very much, Chris. It was really great getting on.